Hello, this is Alex Voss, your professor in TVE course, and I want to welcome you to our section on transistors. And what a better place to do it than where I am right now, the campus of Texas Instruments. Texas Instruments is one of the largest manufacturers of semiconductor products in the world and premier in the development of semiconductor and transistor technology. They started transistor technology production back in the 1950s, and they're well known worldwide for their influence on semiconductor and transistor technology. Well, let's begin our course and have fun learning about transistors. Hello everybody. I was really surprised by all the interest we had in transistors and the comments and the huge amount of people watching the TVE course transistor section, which was just a overview. I'm going to go into a basics of transistors here and start with some of the things you probably need to know the most, and then in the part two of this being part one, we're going to actually talk about basics still, and then in part two we'll get more into the math and things like characteristic curves and so forth. And what I wanted to start with was a little review about the diode. Now, a diode is a solid state. Well, it could be a tube too, but in this case we're in solid state, and we're talking about solid state like germanium, or there's some other materials that we could use, but we're going into solid state. And right here I have a picture of a diode, and it's a schematic symbol, and this device only allows current to flow in one direction. The current's only going to flow this direction. It flows from the cathode to the anode. So when the current flows this way, it's causing a vacuum over here, making this positive if you're making a power supply, because electrons are being pulled in this direction. Diodes only allow electrons to flow in one direction, from the cathode to the anode. In 1874, solid state diodes are not all that new. In 1874, a German scientist called K.F. Braun discovered the unilateral conduction of crystals, which means crystals would allow current to flow in one direction but not another. Some crystals only would allow current to flow in one direction automatically. That's how we came up with the cat's whisker for the cat's whisker radio that allowed us to demodulate amplitude modulation in the early days of radio. And an Indian scientist called Chandra Bose, Jagadish Chandra Bose, was the first to use a crystal for detecting radio waves. And he did this in 1894, and this was a primitive solid state diode made of galena. And then later on, they had the tube diodes, but they were problematic. They would break down, and they ran hot. They used a lot of energy, and so they were looking for solid state diodes that would handle power. And so they came up with a copper oxide and selenium rectifiers that they made in the 1930s. And in some of the older sets, you'd see these big old things with many different squares. It was like it would look like this. Basically, you'd have a wire coming in, and you'd have many different plates, and it's a big rectangular square thing, and that was a selenium rectifier. You don't hardly see them anymore, but that was what they had to use before they had the solid state silicon diode. And of course, the silicon diodes were invented in the 1940s, and there's a lot of interesting history there. Okay, let's move on to our next topic. A transistor. We're going to be talking about transistors now. And transistors are fundamental to the understanding of modern electronics. I mean, in 1947 and 48, when the transistor was invented, they had tubes and they had electronics, but when the transistor really came into its own, starting in the early 50s and then the 60s and 70s, it made a huge change in the modern world. You could not have the things we have in our modern world without transistors. IC chips are made of billions and billions of transistors sometimes, depending on the IC chip. And so transistors are fundamental to our society now and to our electronics. A transistor is basically a three-terminal solid-state electronic device that is used for amplification. Amplification is where you take a small signal and make it into a larger signal. And before that we had tubes to do that. And in some cases they would use relays to take a small current and switch a large current, but that wasn't really a signal as much as just turning something off and on. Now transistors can be used as switches too, but the neat thing about transistors is they can vary the output when the input varies, so it's not just off and on, it could be anything in between. A transistor is a three-terminal solid-state electronic device that is used for amplification and switching. It has three elements: an emitter, a base, and a collector. It also can be called a bipolar junction transistor. This is a picture of a transistor here. This transistor is a power transistor. It's a medium power transistor. And you'll notice it has this tab on the top. This tab on the top is called a heat sink. A heat sink is there because a transistor is not totally efficient. And so what happens is if you don't dissipate the heat, the transistor will overheat and stop working. So you always have to have a cooling system in many of these transistors, because when they're pulling a lot of power, a lot of that is going to be turned into heat because of the inefficiency of a transistor. We try to make them as efficient as possible, but it's not totally easy to do. And these three leads would be, depending on the assignment on the transistor, an emitter, a base, and a collector. This is a simplified amplifier. I just wanted to just look at the basics of an amplifier here. And this amplifier would be a common emitter amplifier, and we call it a common emitter because here's the emitter and it's common to both the input and output. A signal comes in on the base and it actually modulates the current flow through the collector and emitter. And it's dropped here. Here's a positive voltage here, or a voltage here, that's a collector voltage, and that it causes a drop across this resistor, and then a signal is seen on this output. Basically, this would be amplifying a little bitty signal over here would cause a larger signal over here. And this is a simplified drawing, and we're going to go into more details in just a little bit. Transistors are current-controlled solid-state devices that conduct current in proportion to an input signal. The transistor on the left is called an NPN, and the transistor on the right is called a PNP. Now, see the arrow pointing out? That means it's an NPN. The arrow pointing in means it's a PNP. Not pointing in transistor, when we say pointing in, we're referring to this base plate here. Not pointing in transistor, pointing in transistor. This is a picture of one of the first solid state transistors ever made. This is a point contact transistor. Now, the very first transistors were point contact transistors, which means that they weren't made out of one piece of material, whether it be silicon or germanium or whatever, but the elements were touching. They were made to touch each other, and when they touched, and if you had the spacing perfectly right, you could have amplification, you could have gain in this device. In Bell Labs in 1947, John Bardeen, Walter Brattain, and William Shockley used a triangular plastic piece of plastic, a triangular piece of plastic with gold on it, and they etched or they scratched a little bit of the gold off the very tip of the triangle of the plastic, and then they put it on a piece of germanium. And when they got it touching just right, it produced amplification. And what they did was they took a microphone signal and they fed it into one side of the transistor, and then they had an oscilloscope on the other side of the transistor, and they could see it was probably a dual trace oscilloscope, so they're looking at the input signal versus the output signal. And then what they found was that the output signal was larger than the input signal, so there was gain, and that was a big deal to them to get that to work. Now also in 1947 and 48 there was two German physicists that had migrated from Germany after the war, and named Herbert Matre and Heinrich Welker. And they invented the transistor almost, maybe a little bit ahead or a little bit behind of Bardeen, Brattain, and Shockley. But Shockley and Bardeen and Brattain got the credit for it, even though historically it may have been Herbert Matre and Heinrich Welker that made the first transistor. But what happened was, PBS had a great series, and it was called Transistorized, I believe. I'll put it at the end of this class, and when I give you some information for further study. And it went into the details of the relationships of Brattain and Bardeen and Shockley, and how they got together and invented the transistor. What happened was Shockley was the one that had the idea. He actually envisioned the field effect transistor, which we actually have field effect transistors today. And so instead of making a point, he assigned Bardeen and Brattain to build the transistor and work on it. And they worked on it for months, many months. And they never could get the field effect to work with the primitive materials that they had at that time. But they eventually, Bardeen was a physicist, and Brattain was also a very good engineer and an extremely good tinkerer, if you want to call him that. And he just kept doing experiment after experiment after experiment, and finally came up with this wedge or this triangle of plastic with gold on it sitting on a piece of germanium, and was finally able to achieve transistors. And actually some of the very first transistors manufactured were point contact transistors. Unfortunately, they had a tendency to break. They were unstable because you're dealing with actual points that were touching a material. This picture here is the French version of a point contact transistor, and it was used in the French telephone system. And the reason they wanted amplification in the first place, one of the big reasons Bell wanted it, was they couldn't send a phone signal much past halfway across the country because there's no way to amplify it readily. Well, they used tubes, but tubes tended to break a lot and so forth. So getting the signal all the way across the country needed a good, better than a tube amplification device. And so that's why Bell Labs was really so excited about, coming up with a solid state amplifier of some kind. Now, what happened was that, Shockley had the idea of the transistor. He understood the physics. He was brilliant. He wasn't a great manager, but he was brilliant when it came to, the concept. And so he assigned Brattain and Bardeen to, build or work on the transistor. And so, but they went in a different direction with the point contact. They didn't really tell Shockley. And they called him up one day early, I think it was early in the morning, and told him that we've got a transistor, it's amplified. They hadn't named it transistor yet. The name for transistor came up a couple months later. But we've got this solid state device that will amplify. And when they told him how it worked, he was pretty upset because he realized that the two guys he'd assigned to build a transistor according to his theory built something totally different, and they actually invented the first transistor, or first amplifying solid state device, but they didn't do it the way he wanted, and so he didn't think he would be able to get credit for it. And that started sort of some harsh feelings between the bunch, and it sort of broke up the team, and there was a lot of discussion between them and the people in Bell Labs that that Shockley sort of took that negatively, that he didn't actually invent the first transistor, or the first transistor wasn't invented the way he thought it should have been. So he sort of broke off on his own and started working on a better transistor now that he realized how it could be done with a point contact. And so on his own, without talking to hardly anyone, without sharing with Bardeen or Brattain or anyone else at Bell Labs, he came up with this idea of a bipolar junction transistor. And basically that's the transistor we have today. And I'm going to put a picture up here where you can see it. The bipolar junction transistor was invented by Shockley in 1951, and you basically take a complete piece of a semiconductor material like silicon or germanium, and then you introduce a dopant. And so what you can do is you can have a material that is the same piece of material, but you can inject a dopant into different regions on this and create a transistor that is much more stable because it's one piece of material. And so it came out in 1951, and a bipolar junction transistor, sometimes called a BJT, consists of three differently doped regions: the emitter, the base, and the collector. And it's on a single piece of silicon or germanium, and an impurity called the dopant is added to it, and to produce a P or N region. Common dopants that are used to create regions of a transistor are antimony, phosphorus, arsenic, boron, aluminum, gallium, and gallium arsenide. Here's a picture of a bipolar junction conceptual drawing. It's a one block of silicon, and what they do is they've doped the whole thing with an N-type material. So they put a dopant to make it all N, and then they put another dopant on the top here that made a P region right here in the middle, and then they put another dopant right here that made this little N region. So it's like whatever they doped it with, it made these three layers. And so now it's one piece of material with three layers. And you have the emitter, the base, and the collector connected to, wiring connected to these three areas. And it would make this another symbol for a transistor. So this is the type of transistor that we have today. And what's amazing about this is almost done as if it's a photographic emulsion, where you're putting chemicals on the material and making a pattern. And so when you do an IC chip, you can actually make a pattern of millions of transistors on one silicon wafer. Now, and you can't see this picture very well, and we're going to switch over to a better picture. But this is a picture of the first point contact transistor. And what we have here is a piece of copper, and then sitting on the top of the copper is a piece of germanium right here. And then there's a triangle of plastic here, right here. And then right down on this side is a piece of gold leaf, and on this side here is a piece of gold leaf. And down here at the very bottom of the transistor, the gold leaf has been scrubbed off in a very thin line, and that's sitting on top of the germanium. And so what happens is we have a connection to this side, a connection to this side, and a connection to this, which is the germanium. And so we can have a large current flow. What happens is this would be the base over here, as I remember. This would be the emitter, and this would be the collector. And so at this point here where it connects to the germanium, a little bitty signal on this side would influence a large current flow up through here and across over to that side. And that is the picture of the very first Walter Brattain built transistor.